So we left off last time balancing, excuse me, not balancing, but identifying the oxidation reduction parts of this equation, of an oxidation reduction equation, figuring out what is oxidized or what loses electrons and what is reduced, what gains electrons. So we're going to kind of rehash that a little bit before we move on. And so we're going to use that same chemical equation as a reminder. Remember, we're using the rules for identifying what's oxidized and what's reduced. We're using those oxidation number rules to assign oxidation numbers to each of the elements in the chemical equation. So for something like zinc, right? Zinc is a lone or free element, so it's going to have an oxidation number of 0. If we look at the copper sulfate, well, we know that sulfate overall has a -2 charge, so the copper has to be +2. Okay, oxygen is almost always going to be -2, and in order for this to be a neutral compound, there are 4 oxygens, which give us a total of -8. Means the sulfur here has to be +6. Okay. Okay. So if the sulfur there is, so there's +6, okay, so we can go on to the other side. On the other side, the zinc, right, so the zinc is attached to a sulfate. Sulfate's -2, so zinc there must be +2. The oxygen doesn't change, it's still a -2. The sulfur is still in part of sulfate, so it's still a +6. And then the copper over here is by itself, so that's a 0. So we use our tie lines, we can see that zinc loses electrons, right? It loses 2 electrons going from 0 to +2. So if it loses electrons, it's been oxidized, so we can say oil. And then copper has gained electrons. It goes from +2 to 0, and so it's reduced, so we can label that Rig. Okay. Now, one other thing we can add to this is the idea of an oxidizing agent and a reducing agent. So the oxidizing agent, it's the reactant that contains the element being reduced. So it's the thing that does the oxidizing because it's being reduced. So in this above equation, the oxidizing agent is the thing that has the element being reduced. The element being reduced, of course, is copper. Therefore, the reactant that has copper in it is copper sulfate, right? And the reducing agent is the reactant that has the substance being oxidized. In that reaction, copper is being reduced. The thing that's being oxidized is the zinc, and so the zinc in this case is going to be our reducing agent. It's the thing that does the reducing. And so that allows us to sort of tie up redox chemistry from the standpoint of identifying what's being oxidized or reduced, identifying the oxidizing and reducing agents, using oxidation numbers to find all of that, and then using, and here in a second, we're going to use our oxidation numbers a little bit more to understand how chemical equations can be balanced when they already kind of look balanced. And so that's our next thing. It's 4.10, balancing oxidation reduction equations. Basically, when we're looking at an oxidation reduction equation, right, it's a chemical equation. It's a reaction that's taking place. But one of the keys here is that we have a movement of electrons, and electrons still have mass. They are still pieces of matter. And so we have to account for that by making sure we don't lose overall any electrons from the chemical reaction. And so if we look at the equation that we have here for our example, it's a fairly simple chemical equation. It's just copper reacting with silver ions to produce silver metal, right? And some copper ion. And so you can look at the oxidation numbers of each of these. So the copper is solid, so it's in its metal state, and so it's going to have an oxidation number of 0. The silver is plus, silver plus, so its oxidation state on the reactant side is a +1. But the silver gains an electron, so it has an oxidation state of 0, and the copper loses 2 electrons, so it goes to +2. And so what we have here is we can identify that copper right, loses 2 electrons. And so we can say, Leo Gur or oil rig notation and the tie lines to identify that. And just as a note, I'm going to say, well, each copper loses 2 electrons. So I'm going to include that in my tie lines. And with the silver, right, that's reduced. Oops, try that again. So GER, right, gain electrons is reduction. And in this case, each silver is gaining 1 electron, right? So in order for this to be balanced, we have to account for the fact that we have a different number of electrons changing places. And if copper loses 2 electrons and one silver atom only gains 1, this cannot be balanced because there's 1 electron out there somewhere. And so we can balance this chemical equation by essentially using a stoichiometric coefficient for one of these to make the electrons add up to the same total, right? So in this case, if we want to, if copper's losing 2 electrons, well, the silver on the whole has to gain those 2 electrons. And in order for that to happen, we need 2 silver atoms for every 1 copper. So we can just go in here and put in a 2 in front of each of the silvers. So each silver ion gains 1 electron for a total of 2 electrons now. And those 2 electrons are coming from the copper, right? And so now we have a balanced chemical reaction that accounts for the electrons being lost and gained. Okay. Now, we'll talk a little bit more about this for some more complicated reactions in the future by doing what's called the half reaction method. And that's something that you'll need more when you do electrochemistry in a Chem 102 course. All right. Yes, Amir.
My question was about copper and silver. Why did you mention both of them as being solid? They were aqueous on the other page, weren't they?
Back on this one. So we had zinc. So here, the copper metal, right? So if you see copper solid, that's copper metal. Silver solid, that's silver metal. So if you have an ion, right? So if we look at, for example, the silver ion here is aqueous. The way you would get a silver ion into solution is having it as a silver salt. So maybe like silver nitrate. When you dissolve silver nitrate in the solution, that solution produces silver ion as silver plus. So essentially what this chemical reaction is as written, this is a net ionic equation.
Thank you.
All right. And that basically takes care of the chapter 4 material. So before we move on, are there any questions on this material? You'll notice I've got a whiteboard behind me now, so I can actually answer those a little bit easier. So if you guys do have questions, sometimes, I'll be able to do that and hopefully make sure you guys can see it all too. All right. Okay, so that was our types of reactions chapter, right? We've done essentially the math, right? Starting in chapter 1, we did math, getting ourselves acquainted with how do we do chemical calculations. Chapter 2, we did a lot of nomenclature work and started to identify matter. Chapter 3, we started to look at stoichiometry of chemical compounds. And chapter 4, we're doing stoichiometry of chemical reactions. So you have all that in your toolbox, and we're going to kind of shift gears now. We're going to talk about one of the states of matter in particular, and that's gas chemistry. And so here, what we're going to do is we will start out chapter 5 with essentially an introduction to some things that we need in our toolbox in order to really talk about gases. So the first thing that we're going to look at here is pressure. So we've talked a little bit about pressure in the past. We've talked about, but really not sufficiently. We've maybe used it here and there. You've done some calculations in the lab, but so far we haven't really defined what pressure is from a really super useful standpoint. And to some degree, what we're going to talk about here is related to things that we're going to see a little bit later on, namely in section 5.6 also. We'll dive a little bit deeper into this. But when we think about pressure, so pressure has a very simple definition, okay? And that simple definition is what you see up here, right, is the force per unit area. And so the force per unit area, what's happening there is if you have a gas sample, right? Let's say that gas sample is in some sort of a volume, maybe a container of some kind. You'll have gas particles, right? So these gas particles, they're moving around, they're moving in various directions, they're moving largely in straight lines, and we'll talk a little bit more about how that works in section 5.6 when we look at the kinetic molecular theory of gases. But some of these gas particles will ultimately hit the walls of the container. And when they hit the walls of the container, they exert some force based on their mass and based on their velocity. And that force is what accounts for the pressure. It's when we talk about the force, it's the average force that you get, right? It's that average force you get per unit of area. Okay, now, when we measure pressure, we'll talk about the units of it in a minute, but when we measure pressure, we measure pressure in largely two ways, and we have different tools for doing this. But if we're measuring atmospheric pressure, we use what's called a barometer. And over here on the right-hand side is a typical barometer. Now, a barometer is made, this is an old school mercury barometer, and there are other ways of doing this now, various types of pressure gauges that rely on calibration from something like a mercury barometer. But the basics of a mercury barometer are the following. You have a tube, right? So this is your tube filled with mercury, and mercury is the liquid of choice here because it's very, very dense, right? So mercury is the only metal that is found in its liquid state under atmospheric conditions, room temperature and atmospheric pressure. And so you use mercury because it's so dense, it's so heavy per volume. And what you would do is you would fill up this entire tube. You'd fill that whole tube up, okay? Now, when you fill that whole tube up with mercury, you fill it all the way to the top. Of course, it would be inverted, right? This is inverted compared to what it would be. So it would be the right side up, okay? And you would fill it all the way to the top. You'd say, cover the top of it, invert it, and stick it into the pool of mercury that you see down here. So you have this pool down there. When you put it into the pool of mercury, the mercury in the tube that's now inverted would try to fall out of that tube and go into the pool. Now, the reason, of course, that it's going to try to fall out of that tube is because of gravity, pulling down on the mercury in the tube. But here, you have this pool of mercury, and pushing down on the pool of mercury is atmospheric pressure. And so the mercury doesn't fall all the way out of the tube. It falls out until the force pushing down on the mercury in the container is equal to the force associated with the weight of this column of mercury from essentially the top of the mercury up here to the top of the mercury in the pool itself. Okay, so the weight of that mercury is pushing down or being pulled down by gravity. And then there's a pressure associated with atmospheric pressure, right, that is pushing down on the mercury in the pool. When those things are balanced, then the pressure pushing down from the atmosphere in this case is going to equal the force, the average force per unit area associated with the weight of the mercury in this column, okay? And at that point, for one atmosphere of pressure, you can measure the distance, right? You can measure this distance here, right? At 1 atmospheric pressure, the distance between the top of the pool of mercury and the top of the mercury in the tube is going to be 760 millimeters. Okay, that unit is also called a torr because of Torricelli is the guy who basically used that as a standard measurement for pressure. Okay, so that's how you get a atmospheric pressure using a barometer. Okay. But in chemistry labs, we often want to measure the sample of a gas, and a sample of a gas is measured, the pressure of a sample of gas is measured using a manometer. So there are two types of manometers. There's an open-ended manometer and a closed-ended manometer. The closed-ended is over on the left. The closed-ended manometer has, again, we're still using mercury, but on the top of the mercury on one end is a vacuum, and on the other end is your sample of gas. Now, the example on the far left shows that there's no gas in the container, but there's also no gas in the end above the level of the mercury, right? That's the idea of a vacuum. There's nothing in there from a particle standpoint. Now, in that case, you're going to have the levels of mercury in either side of this particular manometer are going to be equal because there is no gas pushing down on the top of the mercury, basically on either side, right there or right there. But if you introduce a sample of gas into a closed-ended manometer, so you have gas over here now, that gas is going to push down on that side, right? The side that has the gas in it, it's pushing down on the mercury, causing the mercury on the other side to go up. And the pressure inside the container on the gas side is going to be dependent upon or measured by the height of the height difference of the mercury on either side. Okay, so at 1 atmosphere, that particular height would be 760 millimeters. Okay, if you have an open-ended manometer, right? So over here we have our open-ended manometer. Here you have atmospheric pressure. Right? So the atmosphere is pushing down on the open end. And if you have a sample of 1 atmosphere worth of gas, right, they're going to be pushing down the same amount, so the levels of mercury will be the same, right? So those will be equal, okay? And so the difference in the pressure in the container with the gas is going to be based on the difference in the height, okay? So on the second example, if we have 2 atmospheres of gas in here, then we only have 1 atmosphere of pressure pushing down on the open end, and so the difference in height would be that second atmosphere, right, of pressure, okay? And so when you have an open-ended manometer, you're looking at the difference in the height being the difference between the pressure or atmospheric pressure pushing on the open end and the pressure inside the gas container. Right, so that's how we measure pressure. Either a barometer for atmospheric pressure, or we have a manometer to measure the pressure of a gas sample. Okay, so as far as units go, you may have seen units of pressure in the past. The SI unit of pressure is the Pascal. Often we'll see, the Pascal is a very small measurement, so it's a Newton per square meter. And a Newton is just the measurement of force, that the SI measurement of force, where it's going to be something that we don't tend to use the Newton very much. But what we do use the Pascal sort of as its unit. We'll come back and look at this from in a derivation a little later as to the units that make up the Pascal, but we'll often, because the Pascal is so small of a unit, we'll often use the kilopascal, right, which is just 1,000 pascals, because it's more on par with the other units that we'll see, okay? The most common unit that we're going to use is an atmosphere. So an atmosphere is just the pressure of, so 1 standard atmosphere is the pressure that you would associate from all of the gases in the atmosphere pushing down on us at sea level, okay? Another 2 that we'll see frequently are the measurement in torr or millimeters of mercury. Okay. So whether torr or millimeters of mercury, those two units are both very commonly used as well, because they're simply how we measure things using a barometer or a manometer. Okay, so they're very commonly used. Now, we'll look at the numbers associated with these in just a sec. Another one that's commonly used that you'll see, for example, in the weather forecast, is we'll have pressure that's often measured in inches of mercury. So you can see that even if you've looked at your good old iPhone, your weather app, it has the pressure measured in inches of mercury, and that's the same as you would get if you were looking at the news, in any given morning. Okay. Other common ones that we see are PSI, so pounds per square inch. So if you've ever measured the pressure in your tires, that's generally measured in pounds per square inch. Okay, so that's your PSI. And of course, if you have a pressure gauge, you can see we got PSI there. Actually, let me change my color there so you can see that a little better. So this is PSI would be on the inside gauge, right? And then this particular pressure gauge has kilopascals on the outside measurement. So you can see those are commonly used there. The other one is the bar. So a bar is essentially just related to the Pascal. It's actually so it's basically the Pascal divided by 10 to the fifth, right? And so basically the bar is much more on par with an atmospheric pressure. They're very similar. So we've got values here, right? The atmosphere, 1 atmosphere is standard pressure, right? Or standard atmospheric pressure, which is the same as the measurement in torr, and the measurement, which is the same as 760 torr, or 760 millimeters of mercury, which is the same as 29.92 inches of mercury. So you can see over here in our weather measurement, right, the pressure is a little bit below atmospheric pressure. So there's a low pressure system on whatever day this weather was taken. We've also got standard pressure in PSI is 14.7 pounds per square inch. And then you can see 1 atmosphere is a little bit less than a bar, or a bar of pressure is just a tiny bit more than an atmosphere. And you can see the bar and the pascals are directly related. Okay, so those are units that we'll encounter regularly. Another thing that sometimes people think of as trivial, but isn't, is the type of container that we have to account for. Now, types of containers are important because, as we're going to see, volume is important. And so volume of the container will have an impact on the pressure of that container. And so understanding where is the container able to move? Is it able to expand or contract, or is it going to be always the same size? And so we have these 2 types of containers to account for. We have flexible containers and rigid containers. And so if we have a flexible container, right, the volume of a flexible container can change. And so it can expand or contract. And so examples of flexible containers, right, we've got our the balloon here, right, or a piston, and a cylinder. Okay, so what we're talking about is the volume on the inside of that cylinder piston combo. Now, when it comes to a flexible container, generally the pressure inside and outside the container are going to be equal. And so that's when we think of a flexible container, that's kind of our go-to, is understanding that the pressures are going to be the same inside and outside. So the gas inside the container, right, inside this piston, is pushing out on the piston, and the pressure from the atmosphere is pushing on the other side. And that piston, if it's free flowing, will move in either direction depending on whether the atmospheric pressure or the gas pressure on the inside is going to change until the two pressures are equal. Okay, so on the inside of this particular piston, right, there's a pressure of 3 bars. That piston would move up and expand until it met the pressure on the outside. In a balloon, we know as with the balloon, it can expand and contract depending upon the pressure. Again, now the pressure on the outside of the balloon is coming from the atmosphere. The pressure from the inside of the balloon is coming from the gases on the inside. And so those are going to be containers that have a volume that can change. When it comes to a rigid container, though, the volume of the rigid container is constant. So it's not going to change, which means that when we look at something that has a rigid container, we're really looking at a constant volume. So we might be looking at how many moles of a gas or how many, what the temperature of a gas is and the pressure on the inside of that container. So some examples of rigid containers, right? You've got metal cylinders, right? So if you wanted to fill up a cylinder with, some sort of gas, like you can get these, red helium containers at Party City, right? Those, you can fill those with helium and the container stays the same size, but as you add more helium to it or take helium out of it, the pressure on the inside of the container will change. Or if you have something like a glass flask, that glass flask can hold a gas and the flask itself is going to have a volume that's set, okay? And we'll see where that's important or where the volume of the gas changing is important versus where the volume of the gas is rigid is important, right? Constant volume or a volume that can change, okay? Okay, so the next thing we're going to look at, we've got some gas laws, and that's the laws of Boyle, Charles, and Avogadro. And so to look at this, what we're going to actually do is, see if I can get my pointer back. Okay, so what we're going to do here is we're going to pull up the PhET simulation website. I need to go find my resources here. So the gas properties one, this one has been converted. So the gas properties PhET simulation is a way of looking at gas. So we're going to use the ideal gas model for us, okay? So we have, when we're looking at this, we have a container. That container is going to have gas particles, which we're going to add by pumping some gas particles into that container. And those gas particles will move around.
Excuse me, sir. Sorry for interrupting. We are still just seeing your PDF. We are not.
Oh, sorry. Thank you. Yeah, I got to reshare. Thank you. So let me go back and redo that. Oy. So 1 second. So you get, okay, so we're here. So what we're gonna, so what we'll do is share this screen. Okay, so if you click on that link, this screen should pop up. Okay, see that now?
Yes, sir, thank you very much.
Great. Okay, so here's the simulation, this PhET simulation. We're just gonna look at the ideal gas simulation. And we can add the gas particles to the container just by using this little bicycle pump here. You can see the gas particles will fill the container and they're going to move around. And we'll use the simulation in a couple of different times. But basically you can see these particles, they move around, right? They collide with each other. The gas particles, they collide with the walls of the container, right? And the collisions with the walls of the container are what account for the pressure. And so up here in the right-hand corner, you can see the pressure gauge. Okay, that pressure gauge is just measuring the pressure of the gas inside the container. Over here, you have a thermometer measuring the temperature of that container. And we have a couple of other factors. One is the volume of the container. Now we're just gonna hold so right now the volume isn't changing. We've just pumped in a gas. We're kind of starting with this, okay? We can monitor how many particles there are, but we can hold different variables constant as we look at what happens in this particular simulation. Now, the other thing we can do is we can make adjustments. If we want to add more gas particles, we use the bicycle pump to increase those particles, or we can change the number of particles by adding them down here. Don't worry right now about heavy versus light particles. We'll come and look at that in section 5.6 when we start looking at kinetic molecular theory of a gas. And so what we can do now is we can monitor how pressure inside the container, the number of particles inside the container, the temperature of the gas, and the volume of the gas are all related, okay? And so the first thing we're gonna do, I'm meant to change the share. We're gonna come back to our PowerPoint slide, and we're gonna start out by looking at Boyle's law, okay? So Boyle's law says the volume of a gas is inversely proportional to its pressure at a constant temperature and constant number of moles of gas. So what we're gonna do here is go back to our simulation. We go back to our simulation to look at Boyle's law. We have two things that are constant. One of them is the number of particles. So I'm not going to change the number of particles here. I'm also going to hold the temperature of the gas constant, okay? So when we think about pressure and volume, this container has a specific volume and pressure associated with it. Remember, the pressure is the average force per unit area of the, in this case, the inside of the container, right? Remember, a container is three-dimensional, so we're looking at the surface area on the inside of the container. Well, if these particles are moving around and their collisions with the side of the container are what account for the force that you get on the inside of the container, or the force coming from a given collision is based on the mass and the velocity of those particles. And the pressure is the average, so it's that force per unit area. If I increase the volume, so I'm going to grab my side of my container, and I'm going to increase the volume. When I increase the volume, right, the surface area on the inside of the container increases. And so the area underneath, right, that or in the denominator gets larger, which means you would expect the pressure, if the volume is increased at a constant temperature with a constant number of moles of gas, you would expect the pressure on the inside of the container to go down, because the average force that you get from the collisions of those particles is now spread over a much larger area, right? Larger surface area. So what you would see there is as the volume goes up, the pressure should go down. And it did. It was at about 6 before, 5, a little bit less than, right around 6, but a little bit less than that. Now, if we've increased the size of the container, it's gone to a pressure of about 4, right around 4. So if we were to cut the size of this container in half, make the container smaller, you would expect the pressure to increase. So if we make it about half, you expect the pressure to essentially double, because the area of the container is 1/2 of the size. So the pressure, and it basically doubles, okay? And so that is Boyle's law for us, okay? So Boyle's law says the volume of the gas is inversely proportional. So this V, that symbol there, right, means is proportional to. So volume is proportional to 1 over the pressure, or it's inversely proportional to the pressure. And another way you can look at that is you can say that the volume is equal to K. In this case, we're going to say KB. So that's going to be our constant associated with Boyle's law. That's KB is just a constant. Okay, and so it's just a proportionality constant. So V is equal to this proportionality constant times 1 over the pressure. Now, if you were to graph just volume versus pressure, you would get a curve, right? And this curve, right, would be decreasing, because we know as volume decreases, pressure increases, right? Or vice versa, as pressure or as volume increases, pressure decreases. But if you were to graph the volume versus 1 over the pressure, you would get a straight line. And that's often one of the things we're looking for in science, is we want to see how things are related by getting a direct line relationship. And so on this particular graph, you could actually find that the slope of this line is going to equal that constant, right? That Boyle's law constant, if you will. Now, we're not going to use a Boyle's law constant. It's not something we're going to use. We're just using that as a theoretical way of understanding how the data for volume and pressure for a given gas sample is related. Okay. All right. So that's our first law, Boyle's law. Our second law that we're going to look at is Charles' law. So Charles' law says the volume of a gas is directly proportional to its temperature at a constant pressure and constant number of moles. And so we're going to go back to our simulation to think about that. So we're back in our simulation now. We're going to reset that simulation. Make sure we got the same number of particles to begin with. And now what we're looking at for Charles' law is we have a constant number of moles, number one. And the other thing we're looking at, so the constant number of moles, because we're not going to add any more moles of gas to it from our bicycle pump. And the other thing is we're going to set the pressure constant. So, okay, so let's hope that I pick the right one. This is a new simulation from what it has been. They've been updating these online fairly regularly, so this is going to be kind of nice to see. So in this case, if we think about the relationship between temperature and volume, holding the pressure constant, if we want to keep a constant pressure, then if we change the volume, the temperature will have to change. Okay, so if we were to expand the volume of a container, the temperature would have to change in order to make sure the pressure changes. So if the volume of the container increases, right, the area of the surface area of that container also increases, which means that you would have to have more force for the particles. And so in order to get those particles to hit the side of the container with more force, they have to be moving faster. They have to have a higher velocity. And so in order to have that higher velocity, you can increase the temperature, which is another thing we're going to look at later on when we look at the kinetic molecular theory of gases. Essentially, the temperature is related to how fast do those particles move. So if we increase the container size, the surface area increases. And so we have to add heat. You can see our little bucket down there, we put a little fire in there to heat up the particles. So we have to increase the temperature in order to maintain the same pressure, okay? If we were to cut the volume in half, actually what we can do here is, so if we cut the volume in half, right, the temperature is going to need to go down. And if you look at the ice bucket here in a second, when I release the mouse button, you'll see that the gas is going to have to be cooled in order to maintain that pressure. So we have our little ice particles, we cool down the gas particles move more slowly so that they're not hitting the walls of the container with as much force. Thus, as the surface area decreased, the force associated with the collisions of the particles with the sides of the container has to decrease as well. Now we can also look at it from the other standpoint. What happens to the volume of the container if we increase the heat here? So if we say if we decrease the heat or increase or decrease the temperature. So if we decrease the temperature considerably, go to minus 42 degrees Celsius in this case, right? Those gas particle, this is not changing like I was hoping. Well, unfortunately, it looks like I can't adjust that on this one this time around. But the whole idea here is if we were to adjust the temperature, right, and increase the temperature, which I can't control right now, I'll have to look at an older version of the simulation in order to do that. Suffice to say that if we were to increase the temperature, the volume would have to increase in order to maintain that pressure. Okay, and so that's Charles' law. Okay, so if we go back to our Charles' law slide, this is a direct relationship, right? So as volume right? As volume increases, or the temperature is going to increase as well, okay? So if we were to graph volume and temperature, we would automatically get a straight line. And if equation-wise, we could say, well, volume and temperature, since they're directly related, we could look at this line, and that line would give us, the slope of that line would give us a constant, where that constant is based on the relationship between the volume and temperature. Yeah, Amir.
Yeah, can you explain the difference between the two graphs? I see what you're saying, but these two leave it a tiny bit confusing.
Yeah, so I'm not done explaining these graphs yet. So give me a minute.
Sorry.
Okay. So when we look at this graph, though, the temperature that we see is related directly to the volume, meaning we have a straight line. Okay. So if we take data at just the Celsius temperature, that's where we have this part of the graph. So if we measure the graph on the right shows the temperature scale in degrees Celsius, okay? If you measure the temperature in degrees Celsius of a volume of gas, let's say at 0 degrees Celsius, you have a gas of some volume here, okay? As you increase the temperature, the volume of that gas will go up. But if you take and decrease the temperature of, again, so if you take and decrease the temperature of that gas, right, then the volume will decrease. At the point that that volume goes to 0, right, is decreased as far as it can possibly go, it intersects the temperature graph at, as you can see, negative 273 degrees Celsius, which if you think about that, right, that would be the Kelvin temperature, where at 0 Kelvin. And so our graph on the left is the temperature measured in Kelvin. Just get my eraser. All right, so that's the graph on the left is the temperature measured in units of Kelvin. The temperature on the right is measured in units of degrees Celsius. So essentially, the Kelvin, or the Kelvin temperature of the gas, right, is the temperature of the gas that we're looking at here, right? So the pressure of the gas is related to the Kelvin temperature of the gas specifically, okay? So hopefully, does that answer your question, Amir?
Yes, sir. Thank you very much.
Great. Okay, so that's Charles' law, the relationship between volume and temperature. The next one we're going to look at is Avogadro's law, and you kind of have more of an intuition for this one maybe than the other two, although the other two are pretty straightforward. With Avogadro's law, we're really looking at the relationship between volume and the number of particles, or the number of moles of a gas. So what we're going to see here is that at a constant pressure and temperature, the number of moles of a gas is proportional to the volume. And you kind of understand that because you have this understanding of what a balloon is, okay? And so let's go back to our simulation. So in our simulation, we're now going to hold the temperature constant. And so the temperature is being held constant here. And what we're going to do, I'm going to actually knock down the number of particles in here. So we have about 25 particles, let's hope. Okay, so here we go. So the volume will change as particles. We're going to hold pressure constant, and the temperature should also be held constant, so we can see what happens to the volume when we say change the number of particles in the container. Okay, so let me just reset this. Let's get our particles back in here. There we go. We're at 50 particles. Okay, we're going to let this equilibrate for just a second. We're going to hold the pressure constant after it's equilibrated. Change the number of particles. Okay, so we've got pressure is being held constant. We're going to see how the number of particles is related to the volume. Too much. So let's just slowly reduce the number of particles in this container. So let's go back here. So our volume, we're going to go to fewer particles. And 25 particles. Hold that constant. We're just going to add a couple of particles here, right? So go to 26, right? Go to 30. You notice that the volume had to increase in order to hold both the temperature and pressure constant, right? Hoping. Okay, so we're going to add our particles back. We're going to take and decrease our volume. This should be a little bit more apparent now. Again, we're going to hold that the pressure constant as we increase the number of particles, right? So if I add a few, wow, this simulation is not agreeing with me. Here we go. There, so, okay, this will be easier to measure then. So we hold that. Number of particles. There we go. Ah, here we go. We can see how the number of particles increase or changes the volume. Now it's working right. So here, if we look at the pressure, we tried to hold the pressure constant, in this case at 336 kilopascals, right? If we remove particles, right? Why is that not working? Okay, so if we remove particles, right, the volume has to decrease as the particles are removed. Or if we add particles, in order to keep the pressure the same, right, the volume has to increase. So if we can think of a balloon, as we blow into a balloon, the pressure is staying the same because it's just the atmospheric pressure pushing on the outside of the balloon is going to equal the pressure on the inside of the balloon, which would be 1 atmosphere of pressure. And so the balloon will expand or contract so that the pressure on the inside and outside are both that 1 atmosphere pressure. So if we blow into a balloon, the balloon expands until the pressure is equalized. And so as we add particles of gas, the balloon must get bigger in order to maintain that pressure. So if we go back to Avogadro's law, we can see that this should give us a straight line where as we add moles of a gas, the volume is going to increase, right? And so in this case, again, we have the slope is going to be going to tell us this constant and how the volume changes as the number of moles of gas also change. Okay. Another way to put Avogadro's law is what you see here down at the bottom, right? So equal volumes of gases at the same temperature and pressure contain the same number of molecules. So the volume is dependent upon the number of molecules, assuming temperature and pressure are directly related. Sorry, if you can hear it, my son is waking up and getting a diaper change, and he doesn't like that in the mornings. So that's what's going on there if you hear that. Okay. So if we put these together, so I want to talk us through this. This is an interesting, or can be an interesting derivation of what's called the ideal gas law. Okay, so the ideal gas law is something that comes out of these 3 gas laws in particular. So if we look at Boyle's law to start out, and we say, okay, this KB, that's a constant, right? That constant shows that volume is proportional to 1 over the pressure, or is inversely proportional to the pressure. In that KB, right, we said, just based on Boyle's law, so if I go back, 3 slides to Boyle's law, we have a constant temperature and number of moles. Those are the things we held constant there. So if I come back to this slide, that constant includes the temperature and number of moles of the gas. Those are not changing, so they're part of that constant. Okay? If we take that knowledge and we say, all right, looking at Charles' law now, well, we've got this Kc for Charles' law. Well, Kc includes the pressure, right, and the number of moles. Well, we already know that pressure is in the denominator because we got that in Boyle's law, right? over here, we know pressure's in the denominator. So we could kind of make up a new thing, okay? We can call Kc equal to Kc prime, which is just a different constant, divided by the pressure, which is being held constant. So now we get this new equation where the volume is equal to this other constant divided by the pressure, which is constant, times the temperature, okay? And so we're starting to figure out more of what these constants are, what's included in those constants. If we now look at Avogadro's law, well, Avogadro's law has this other K, Ka, and included in that constant are constant pressure and temperature. But we also know, based on both Avogadro's law that has pressure in it and the temperature, which is included in Charles' law, we know that the pressure is in the denominator and the temperature is in the numerator in its relationship with volume. So now we can make this new constant that's related to that Ka, and this new constant, we'll call it Ka prime, that now includes the temperature and pressure in the numerator and denominator respectively. So now we have this new equation that says the volume is related to the pressure, the temperature, and the number of moles in that order. And if we take that and run with it a little bit, that Ka prime actually has a special name, and that's given its own symbol, R. So here you can see the relationship here. Volume, okay, is equal to R, or this constant, times the temperature, times the number of moles, divided by the pressure. And if we rearrange this, we get what we call our ideal gas law equation, or ideal gas equation, and that's PV equals nRT. Now, that is going to govern many of the calculations that we do with gases, relating their pressure, volume, right, and number of moles and the temperature. Okay, so there are two versions of R. The one we're going to use most, at least in this class, is this R version that is 0.08206 liters times atmospheres divided by moles times Kelvin. And so the key difference between these two values for R is the units, because the other version of R, you can see down here, is measured in joules per mole Kelvin. So really we're looking at the units in the numerator as being what changed between these two things. And we're going to go through a derivation of this a little bit later when we start to look at when the second version of R is going to come into play. But for now, we're going to stick with the 0.08206 liters atmospheres per mole Kelvin, because that's going to be the most important one for dealing with pressures, volumes, temperatures, and number of moles of a gas. And we will have some examples coming up very shortly where we'll start to utilize this relationship. And one of the keys to this, is we can use this ideal gas equation to compare changes to the properties of a gas. Okay, so as you can see, we can rearrange the ideal gas equation so we can get all of the variables on one side, namely the PV over NT. And those will equal, right, R. So those will equal a constant. And so whatever pressure times volume over moles times temperature you get, it's equal to R. And since PV over NT is constant, then that relationship under any one set of conditions, right, will equal that relationship under any other set of conditions. And so if we give those subscripts for the first set of conditions with a subscript of 1, and for the second set of conditions with a subscript of 2, we get this relationship P1 V1 over N1 T1 equals P2 V2 over N2 T2. And so we can use that to look at those three gas laws and we can simplify that. So to look at the three gas laws, let's start with Boyle's law over here. Okay, so Boyle's law. We have a constant number of moles and a constant temperature. Well, if I have a constant number of moles and a constant number or a constant temperature, well then N1 equals N2 and T1 equals T2. And so these two things essentially can go away. They get canceled out because they're the same on either side of the equation. And it simplifies Boyle's law to P1 V1 equals P2 V2. If we look at Charles' law now. So Charles' law has a constant pressure and number of moles of gas. And so in this case, P1 equals P2 and N1 equals N2. And so we can get rid of those things because they're the same on either side of that equation. And that equation then simplifies at a constant pressure and number of moles to V1 over T1 equals V2 over T2. And so that shows Charles' law. And so if you have a gas that you change the temperature, you can calculate the new volume of that gas. And then for Avogadro's law, right, we've got a constant pressure and temperature. And so the pressure and temperature there, right, pressure and temperature there, right, P1 equals P2 and T1 equals T2. Okay, so if those are the case, you can get rid of them as well, right? And that simplifies the ideal gas relationship for this gas before changing the volume and number of moles to V1 over N1 equals V2 over N2. You can find other relationships as well. You know, there's the Gay-Lussac law, which is a similar version of this relating, I believe it's pressure and temperature, but basically you can find all kinds of different relationships based on which of these variables is constant. And so the next thing we're going to do, we're going to get into an example problem. Okay? And so in this example problem, we have a sample. Our gas sample is a gas bubble, which has a volume of 0.650 milliliters at the bottom of a lake, where it has a pressure at the bottom of the lake of 3.46 atmospheres. What is the volume of the bubble at the surface when the pressure is 1 atmosphere? So here, what we see is a relationship between volume, right, and pressure. The volume-pressure relationship we know is based on Boyle's law. Right, so Boyle's law tells us P1 V1 equals, P2 V2. Come on. There we go. And so here, to do this calculation, if we just figure out what we know and what we are trying to figure out, so we find P1, V1, P2, and V2. Well, our initial pressure, we said, is 3.46 atmospheres. And our initial volume is 0.650 milliliters. Okay. P2 is 1 atmosphere, so 1.00 atmosphere. And V2 is what we're looking for. So in this relationship, you can use units of atmospheres or torr. It doesn't really matter as long as you're consistent. And you can use volumes, whether they're milliliters or liters. It doesn't really matter as long as you're consistent in this type of a question. So with Boyle's law, since we're not dealing with temperatures and different temperature scales, the volume and pressures, they transfer directly. Right, so you can keep them in the same form, right? In other words, zero pressure is zero, whether it's an atmosphere or in torr. The 0 point's the same. Volume, the volume's zero volume is the same, whether it's in milliliters or liters. And so what we're going to do, we're just going to put down what we know into that equation. So P1 is that 3.46 atmospheres times V1, 0.650 milliliters is equal to P2, 1.00 atmospheres times V2. Divide by 1 atmosphere. The units are going to cancel here, right? And so now you can figure V2 will be 2.25 milliliters. Okay. And so that relationship is useful for any time you're dealing with just pressure and volume only. Okay.
Question.
Yes.
How did you know that you have to use Boyle's law and not the other two laws? On this one, I didn't get that.
Yeah. So that was where if we have volume and pressure, the relationship between volume and pressure, here, we'll go to this one, right? The relationship between volume and pressure is Boyle's law. So we'll actually go up to here, right? So volume is inversely proportional, right, to its pressure. So that's what Boyle's law deals with. So that's how you know. It's what are the two things that are directly related. Right? So Boyle's law is volume and pressure, right? Charles' law is volume and temperature. Avogadro's law is volume and the number of moles of a gas. Although, what I'll tell you is that you can use this relationship here in either case, and you just cancel out whatever variables are constant. That relationship should always work. Okay, let's go to another example. All right, so if we now have, say, a piston, right? A piston is a container that the volume can change, right? A bubble is a volume, the volume in the bubble in the last example is one that can change. So these are both examples of flexible containers. So here we have a volume initially of 25 liters at a temperature of 45 degrees Celsius. Okay, it's expanded to a new volume. So our new volume here, 55.0 liters. So in order to expand it to that volume, what does the temperature of the gas have to be? And so here, it's a relationship between volume and temperature. Volume and temperature means it's Charles' law. Okay? And so here, for Charles' law, we've now got V1 over T1 equals V2 over T2. And so this, you can start listing V1, T1, V2. Come on. And T2. So V1 we see is 25.0 liters. T1 is 45.0 degrees Celsius, but that's something we have to convert because our 0 point is based on the Kelvin temperature here. So you have to add 273.2, right, Kelvin to that. And so you wind up with a value of 318.2 Kelvin for T1. V2 is just that, try that again, 55.0 liters. And T2 is what we're looking for. So here we just plug them in. 25.0 liters divided by 318.2 Kelvin is equal to 55.0 liters over T2. And so T2 will equal 55.0 liters times 318.2 Kelvin divided by 25.0 liters, right? Liters cancel, and you do a little bit of math, and you wind up with 700.0 Kelvin. Okay. And if you want to find the Celsius temperature, of course, you just subtract off the 273.2. Okay. So that's our example showing Charles' law. And of course, if we had an Avogadro's law, you do the similar thing.
So can I ask you a question regarding the last question that we were doing? Why,
after that?
yeah, why did you have to change the temperature to Kelvin? That's, I didn't get it.
So the temperature and volume are related based on the Kelvin temperature of the gas. So as we saw up in this relationship, right? When volume is 0, right? When the Kelvin temperature is 0, right? So that's the direct relationship between the volume and the Kelvin temperature of the gas. So you have to make sure that your temperature is in Kelvin if you're comparing directly the volume and temperature of a gas sample.
Since we are talking about the ratios and on both sides of the equation, it will be the same units. We still have to change it just because of the 0 Kelvin that you just explained, right?
That's right, because the if you look at it this way, right? When you start dealing with negative temperatures, this doesn't work, right? Because if you have a negative temperature on one side, you can get a calculation that would lead you to having a negative volume, and a negative volume is not physically meaningful, right? There's no thing, right?
Thank you.
My question?
Yes, so I guess the first step in doing these problems is to figure out which law to use, correct? So just look for the variables. Okay, I'm looking at volume, I'm looking at temperature, and then if we need to convert before we start, doing the math, correct?
Yeah, so if we go back to this relationship here, right? That's what these are all based on. It just happens that if you have in here, right? If you have in here, the pressure and moles aren't touched upon at all. If those are held constant, then you're dealing with Charles' law, right? If you're talking about the moles and temperature that are held constant, you're dealing with Boyle's law. If you're dealing with the pressure and number of moles constant, it's Avogadro's law. So you can basically figure out which law it is using, right, this relationship, right? And figuring out what things are constant and what things are changing, okay?
So if all else fails and we don't know which one to use, we can always use that giant one and just get rid of all the other variables. Okay.
And this is the application of the ideal gas law. So they all fall under this. Now, which specific gas law? Well, then we're not talking about the ideal gas law, and you should be able to pull that out, whether it's Boyle's law or Charles' law or Avogadro's law, based on what you're comparing, basically. All right.
One more question can I ask you? So
Right.
do we have to always change the temperature to Celsius to Kelvin, or only in Charles' law, since it starts at 0 temperature?
If the temperature is constant, you don't have to worry about it, right? This relationship here, right? This is based on the temperature here and here. That's based on the Kelvin temperature. If that's constant, it doesn't matter, right? Whether it's 25 degrees or 500 degrees, if it's T1 and T2 are equal, those values go away. They divide out. And so when you're dealing with Boyle's law and the temperature's constant, the temperature doesn't matter what units it's in because those units are going to cancel out anyway. That makes sense?
Yes. But in Charles' law, the temperatures are not the same, right? Because you changed it.
That's right. It has to be in Kelvin when you're about Charles' law. Now you can graph data, right, based on Celsius and temperature and volume, right? But graphing data isn't the same as doing a calculation.
Yeah. Thank you.
So Professor, you can technically give us a problem where the temperature is constant, but we would use like Boyle's law, for example, if like that doesn't come into play. If it's what you're saying, if the temperature is constant and we use Boyle's law, then the temperature would not be used in the final
Essentially,
equation?
yeah.
Okay.
Yeah, so like, let's say you had a temperature of 10 degrees Celsius, right? At 10 degrees Celsius, if you're dealing with a change in volume and pressure and that temperature is held constant, whether it's 10 degrees Celsius or whether it's 283 Kelvin, right? In either case, you still can get rid of those because the temperature will be the same before and after. Yeah.
Got it. Okay, thank you.
Mm-hmm. All right, so let's look at another example and see how moles are related in here. Right, so this says, in this example, we have a spherical balloon that's inflated to a volume of 30 cubic meters. Notice this volume is not measured in liters at this point, but our relationship has been using volumes that are measured in liters. So we have a spherical balloon is inflated with helium to a volume of 30 cubic meters. If the pressure inside the balloon is 740 torr and the temperature is 27 degrees Celsius, what is the mass of helium in the balloon? And so a key take home here is sort of identifying, right? You're given a volume, 30, try that again. You're given a volume of 30 cubic meters. You're given a pressure in torr. You're given a temperature. And you want to know, in this case, it asked you for a mass. But the mass isn't necessarily directly related for any given gas. But what is related is the number of moles. And so this, if you're given the volume, in this case in cubic meters, the pressure, in this case in torr, and the temperature, you can think about this as being an ideal gas law question. Okay, and so on this one, we know that we're using the relationship PV equals nRT. Okay, now what we know here is, well, if I want to find the mass of something, I need to know the moles of it first. So we need to know, so to know the mass of helium, we must find the moles first. Okay, and so for this, we're going to go and say, well, so P, V, N, R, and T, since those are the variables in the equation. We know our pressure is 740 torr, 0.0 torr. Our volume is 30.0 cubic meters. N is what we're looking for initially. R is 0.08206 liters, atmospheres per mole Kelvin, right? That's our constant. And the temperature is 27.0 degrees Celsius. So here's the thing though, because all of these units are specific in that ideal gas constant, we have to change those units. So we need to get the volume into liters. So volume is 30 cubic meters. So on that one, we need to change meters into decimeters because a liter is 1 cubic decimeter. So to get from meters into decimeters, 1 decimeter is 0.1 meters, and I have to cube that whole thing. And then I know that 1 cubic decimeter is 1 liter by definition, right? And that's one you guys should know by now. Then you can get a volume of 3.00 times 10 to the 4th liters. The pressure here is in atmospheres, right? And so if the pressure is in atmospheres, we can change the pressure from torr to atmosphere by the relationship of 1 atmosphere is 760 torr. Okay, so you get a pressure of 0.9737 atmospheres. And then temperature is in Kelvin, so we have to add 273.2 to this. And so you get a value of 300.2 Kelvin. And so what we'll do here is we're going to stop here. We're going to have these values for volume, pressure, and temperature. And we'll utilize those tomorrow at the start of class to finish this example where we find the mass of helium in the balloon. Okay. So with that being said, we will end our lecture for the day, and we'll pick it up tomorrow. Okay.